My name is Anil Nair, and I'm going to discuss machine learning for measurements of gas properties in rotating detonation engine exhaust flows using laser absorption spectroscopy. Our motivation is to study detonation-based propulsion, which has several theoretical advantages compared to conventional rocket propulsion. These advantages, however, have been difficult to confirm in practice. This is likely due to the complex and unsteady flow field in these combustors, which motivates an acute need for diagnostics. The diagnostic challenges here include the intense thermal environment, which makes laser-based diagnostics very convenient as they are not directly interacting with the flow like thermocouples and pressure transducers do. Additionally, there are extremely short timescales in these combustors on the order of kilohertz due to the supersonically propagating detonation waves. This motivates the need for a megahertz range sensor. Our approach uses laser absorption spectroscopy, or LAS, due to its non-intrusive nature, high speeds, and quantitative value. We recently made megahertz measurements of temperature, pressure, and CO concentration at the exhaust of a rotating detonation rocket engine. Now we'll discuss how we measure these gas properties. Laser light is sent through a fiber optic cable towards the exhaust plane of a rotating detonation engine, where the light is sent through the gas and back to a detector. We can see some of the signals from this detector. In black, we have the signal on the detector before gas is present in the laser beam path. And in orange, we can see the light signal once gas is present and absorbing certain wavelengths of light. We can convert this to an absorbance spectrum, and the two areas in this absorbance spectrum can be used to measure temperature. The pressure of the gas can be measured based on the width of these features, and the overall area can be used to measure the number density of the absorbing gas, in this case, carbon monoxide. We can see some sample measurements of temperature, CO concentration, and pressure at the exhaust of this engine. Our goal in this work is to see if we can use machine learning instead of spectroscopic techniques to measure these gas properties from the raw optical signal. Our machine learning approach involves taking an optical signal from a single measurement period and dividing it up into 250 segments. These become our feature vector. We then take the temperature, pressure, and CO number density from the spectroscopic fitting associated with this measurement. This becomes the output associated with this input. We do this for 80,000 measurements, and then we take 5% of those measurements, in this case 4,000 training examples, and use that to train our machine learning model. In this work, two machine learning models were assessed. One is an elastic net regressor. For this regressor, we chose low regularization, and we preferred to use L2 regularization, as we saw that this reduced the root mean squared error of the results. The second model is an MLP regressor, or neural network, where we use 120 neurons with 2 hidden layers. We can assess the performance of these models by plotting the known values of temperature, pressure, and CO density versus the values predicted by the model. We can see that there's no clear correlation between the predicted temperature and known temperature using the elastic net model. And the same goes for pressure and CO density. This is accompanied by high root mean squared error values. We can also look at the results of the MLP regressor, and we see a more clear correlation between the known values and predicted values. This is accompanied by lower root mean squared error values. We can also compare the REC curves for these two models. We can see that the REC curve for the MLP regressor increases more quickly than the elastic net model, meaning that the MLP makes more correct predictions. We can also compare the results of these models in time-resolved fashion. In black, we have the known temperature, pressure, and CO density versus time. In blue, we have the results from the MLP regressor model, which closely matches the known data. In red, we have the results from the elastic net model, which don't match the known data very well and seem to hover around the average value of the data. In summary, we found that machine learning can be used to accurately obtain gas properties from raw light absorption traces. We also found that a neural network is better suited to this than a linear model. This is likely due to the several nonlinear relationships that exist between spectroscopic parameters and gas properties. We also found that number density and pressure are more easily fit than temperature. This is likely due to the fact that these two metrics are linear with respect to the data compared to the temperature, which has a nonlinear relationship to the data.